Okay, very good morning, one and all. So actually today I'm suffering with some video issue. Okay. Okay. Anyhow, let us start the session. Today we can discuss the fifth chapter. So in the last class we already completed the fourth chapter. The last topic is the channel capacity calculation using various discrete channels as well as the Gaussian channel. We completed all those channel capacity calculations and everything. Now today we can start the fifth chapter. So actually in this fifth chapter we will study about study mainly about the channel encoding techniques, namely the linear block codes and convolutional codes. These two. Okay, so coming to our fifth chapter, here we will discuss about the block codes and convolutional codes. So in general, these two codes, the block codes and convolutional codes are the types of channel encoding techniques. These are the two types of channel encoding techniques. So actually we have discussed it in the first chapter. So already I mentioned I have shown you the same block diagram in the first chapter where I told you the elements. So in the elements you can see, in the elements of digital communication system, you can observe the channel encoder and channel decoder. Okay, so these two comes under, so under the transmitter section as well as the receiver section respectively. So this channel encoder is it's followed by source encoder. So it is followed by source encoder at the transmitter section, and the source decoder is followed by channel decoder. Now I think you are thorough with the importance of source encoder and source decoder. Here source encoder and source decoder are used to avoid the redundancy problems. Are used to avoid the redundancy problem, and it reduces the bandwidth because we can be able to reduce the number of bits by using source encoder techniques. Okay, so that's why source encoder and decoder are very much used. These are used, the source encoder is generally used for compression techniques. Okay, and for decompression, source decoder is used. And here there are two types we discussed. Those are the lossless compression techniques, namely the Shannon-Fano coding and Huffman coding techniques. So we studied all these in the fourth chapter. Now, in this fifth chapter, we will focus mainly on channel encoder and channel decoder techniques. Channel encoder and channel decoder techniques. This channel encoder and decoder techniques are mainly used to avoid the problem of the occurrence of bit errors. So we know that if there exists, for example, if you want to transmit the data bit 1, but instead of data bit 1, if it's represented as data bit 0, or if 0 is transmitted instead of 0, if we receive the data bit 1, then there occurs an bit errors. So in order to avoid that type of bit errors and to detect and so these channel encoder and decoder techniques are especially used to detect the location of bit errors. Detect the location of bit errors and to eradicate that problem. Okay. Then, so let us discuss these channel encoder techniques and channel decoder techniques in this fifth chapter. Okay. Here in this already we discussed. See here you can see. In this slide, you can see the location of channel encoder and channel decoder techniques. Already here I mentioned the main theme of channel encoder. So here this channel encoder, it systematically adds some redundant bits. What it will do? It systematically adds some redundant bits or check bits to the information sequence obtained from the source encoder. So source encoder generates some information sequence. So to identify the bit errors, generally some redundant data bits, these are generally called as check bits. These are added systematically to overcome the problem of bit errors. Okay, or you can say that interference which will that encounter in the channel, that exists in the channel. So to avoid this problem, what we are doing, we are adding some check bits to the information sequence. Now the amount of redundancy using k check bits is added to the n bit sequence. Then you will get n comma k code word. So coming to your fifth chapter, you need to solve this kind of problems, okay, where a 7 comma 3 code will be given or some n comma k. So n is the like size of the code word, okay, and k is the number of check bits added. Check bits added, okay. So here already I told you that this ratio k by n is called as the code rate. It's called as the code rate. Okay, and the amount and the reciprocal of that code rate is can be defined as the amount of redundancy. The amount of redundancy. Okay, so channel encoder just adds some check bits to the original message sequence. So whenever anyone asks you what is the importance of channel encoder just adds some check bits to the information sequence. Information is nothing but message bits. For example, if the message is like a message bit, for example, if I told number of messages are 4 in చెప్పామనుకోండి m. So m is equal to 4 and the number of messages are 4 అంటే it means that we have 2 power 4 combinations. How many combinations are there? 2 power 4 combinations are there, which is equal to 16. Okay, so it range from 0000 to 4 months. Okay, so like this channel encoder just adds some check bits to the information sequence or message sequence. Okay, so here you can write this message sequence as some like this. Okay, so channel encoder just adds check bits to the information sequence to overcome the effect of bit errors. Okay, so in this we studied in the first chapter, and channel decoder is used as the receiver. It is used to reconstruct the original sequence. It is used to reconstruct the original sequence from the like obtained code word. Okay, from the received code word we will be able to reconstruct the original information sequence. Okay, and it uses the knowledge of code used in the channel encoder. The redundancy contains in the received bits. అంటే మీకు చెక్ బిట్ డేటా ఇన్ఫర్మేషన్ తెలియాలి. అంటే ఫర్ ఎగ్జాంపుల్ నెంబర్ ఆఫ్ చెక్ బిట్స్ ఆర్ 3 అంటే you will have total of 2 cube combinations. That is 8 combinations ranging from 000 to 111. Okay, so it uses the knowledge of code used in the channel encoder as well as the number of check bits used in the encoding process. Okay, so channel decoder should need this kind of idea in order to reconstruct the original information sequence. Okay, so this is all about the channel encoding and decoding, basic idea about the channel encoding and channel decoding techniques. Now let us discuss the different types of channel encoding techniques and decoding techniques in this 5th chapter. So let us move into the concepts. Here these are the contents of your 5th chapter. Here in the part A, if you clearly observe, part A, linear block codes. Part B is convolutional codes. These two coding techniques are the types of channel encoding techniques. And coming to the linear block codes, here you will see the linear block codes like matrix description. So various kinds of matrices we'll study here, and error detection and correction capabilities of linear block codes. So how can you detect the location of error and how can you be able to correct it? The best example of these linear block codes is Hamming codes. Okay, and block codes, the second type is binary cyclic codes. Okay, so block codes are once again classified into two types. One is a linear block codes. Otherwise, actually here we should not mention the heading as linear block codes, because here we will study two different kinds of uh, like block codes. So in the part A, we will study two different kinds of block codes. One is a linear block code, okay, and the other is cyclic codes. Okay, these are the two different types of block codes. Okay, part A we will study two different kinds of block codes. One is linear block code, second one is cyclic codes. For both the coding techniques, we will study the general encoding process and the decoding process. So while describing the matrix form, we will study the encoding and decoding process of linear block codes. Similarly, for cyclic codes also, we will study the encoding and decoding process. And here syndrome, it represents that it is an error. Syndrome is the difference between the output and input. Actually, so wherever if there is no noise or no error, output should be equal to input. But if there exists any error or syndrome, then there exists some difference between the output and the input. So that difference is generally called as syndrome. So syndrome is the difference between the output and input. So if it is noise free or error free, syndrome should be 0. What is syndrome? Syndrome is an error that can be calculated by taking the difference between output and input. So whenever there is no error, no bit errors or no noise, then syndrome is set to 0. Okay, so next is BCH codes. Okay, so these codes all comes under the block codes. Next part B, we will study the convolutional codes. Okay, so here the the time domain and transfer domain approaches will be studied. And the encoding process includes the state, tree and trellis representation. So here there are three types of encoding, convolutional encoding process. One is the state diagram representation, tree diagram representation and trellis formation. These three are the three different types of graphical approaches. Or you can say the encoding techniques of convolutional codes. And next is decoding using Viterbi algorithm. Decoding using Viterbi algorithm. Okay. So this all we will study the convolutional codes. So generally మనకి convolutional codes the exams, if I want to say the final exams, you will get questions, you will get almost all direct questions from this last chapter. So convolutional codes ఏంటంటే they may ask you to write the time domain and the transfer domain representation of convolutional codes అని అడగచ్చు. And or represent the state, tree or trellis diagram for one example they will give you. And Viterbi algorithm general concept అడుగుతారు మా మీకు ఇక్కడ. Okay, but in the part A we'll get like a problem. It's completely a problematic path. Okay, it is very easy. Okay, so anyhow we can go in detail. In the first module, we'll study the introduction, the matrix description of linear block codes, and similarly the error detection and error correction capabilities of linear block codes and Hamming codes. Actually, this Hamming codes is an example of linear block codes. So in the actually I have split this whole first part A into only two modules. First module comprise of the concepts of linear block codes and the second module consists of the concepts of cyclic codes. And third module whole convolutional codes. Okay, So all this we can study in the further classes. So in the module 1, as I already told you, I have represented the whole linear block codes as the first module of 5th chapter. Here you will study the matrix description of linear block codes and also the error detection and error correction capabilities of linear block codes and the example of it, which is the Hamming code. Okay. Now, already I told you the importance of channel encoding techniques. So this channel encoding techniques, the main purpose is to increase the resistance of digital communication systems to channel noise, to increase the resistance. So, so that we can reduce the error, bit errors, so occurrence of bit errors via the channel. So that's why this channel encoding techniques plays a major role. Okay, and what type of procedures are used? So you can map the input sequence. Okay, you can map the input data sequence into, you can map the input, or you can say incoming data sequence into channel input sequence. Actually what you are doing, the source encoding data is applied to the channel encoder, and this channel encoder adds some check bits, adds some redundancy bits or check bits to the actual source encoded data. So the incoming data sequence is like some check bits are added so that it is suitable to the channel. Okay, and inverse mapping is done at the receiver section. So upon adding some check bits, sorry. Upon adding some check bits, you can increase the redundancy. Okay, third point is upon adding the check bits, you can improve the redundancy. But even though this redundancy is increased, we can be able to detect and correct the error locations. Okay, so redundancy is added, but here you can be able to detect and correct the error locations. The same block diagram which I have showed you earlier. So before channel encoder, actually you will have source encoding process, and in the channel encoder some check bits are added, as I already told you. The channel encoder accepts the message bits and adds a redundancy to produce encoded data at a higher bit rate. So the bit rate is increased because you are increasing the redundancy. So once the bandwidth is increased, so you can increase the bit rate or the information rate. So the channel decoder will use the redundancy to decide or to recover the message bits Okay, and this forward error correction. So forward error correction can be done by using this channel encoding process. FEC, it is represented as FEC, forward error correction. Okay, this forward error correction, error bit detection and correction can be done by using this channel encoding process. Okay, and this this is a discrete channel. Once again, it consists of modulator, channel, as well as the demodulator section, and noise is the signal gets disturbed with the noise during the passes, so during the channel. Okay, so the 2 points that you should remember is channel encoder will add some check bits or redundant bits that will increase the bit rate. That is the first point. And the second point is here forward error detection and correction can be done by using this channel encoder process. Please remember those 2 points. So channel encoder will take the message bits and systematically adds the check bits to produce the data, encoded data at a higher bit rate. That is the first point. And second point is, here the forward error correction can be done at the channel encoding process. Okay, forward error detection and correction can be held at the transmitter section, and at the receiver the opposite functionality of encoding process will be done, and using that redundancy, using the redundancy bits or the code words obtained at the receiver, we can recover the message bits at the channel decoder. Now, so what are the implications of error control coding? So actually there exists, every like uh, every processor will have some pros and cons. So some advantages and some disadvantages. So similarly, even though channel encoding techniques can be able to detect and correct the forward bit errors, that is called as forward error detection and correction, but it has some implications like some drawbacks. So addition of redundancy implies the need for increased transmission bandwidth. Okay, so bandwidth will be increased. So addition of redundancy increases the transmission bandwidth. This is the first drawback. And the second drawback is, it also adds a complexity in the decoding operation, because once the check bits are added for each set of message bits, so the total number of bits will get increased because there exists a redundancy. So it may add some complexity in the decoding operation. Okay, that is the second drawback. And third drawback is, we need to provide a trade-off. We need to provide for these two reasons, for the first and second two reasons, because the bandwidth is increased and complexity is also increased. We need to provide a trade-off between the signal, the SNR. Okay, you can say the error performance. So error performance should be in such a way that our system should be able to should be compatible with that. Okay, so here that's why you need to provide a trade-off between the SNR, error performance, bandwidth, and the signal complexity or the system complexity, signal as well as the system, because signal is also gets affected here because redundant data bits are added. So what are the two implications of error control coding? Because of the addition of redundancy bits or check bits increases the transmission bandwidth. This is the first drawback. And the second drawback or second implication due to error control coding is, it increases the complexity in the decoding operation. Okay, so for that purpose you need to provide a trade-off between the SNR, error performance, bandwidth, and the system complexity. Okay, so advantages are, you can provide a forward error detection and correction. Okay, and next thing is, here by adding the redundancy bits, you can provide the higher bit rate. So number of bits transmitted per second you can increase. But drawbacks include the increased bandwidth and increased complexity in the decoding process. So to overcome all this, we need to provide a trade-off, as we have provided a trade-off for SNR and bandwidth in the source decoding process. So already I told you in the Shannon-Hartley theorem, we have provided a trade-off between the SNR and bandwidth. So R max is equal to 1.44 S by eta అని చెప్పి prove చేసాం. That is the trade-off between bandwidth and SNR in the source encoding process. Okay. So similarly, in the channel encoding process also, we need to provide a trade-off between the signal to noise ratio, error performance, bandwidth, as well as system complexity. Okay. Next, there are two types of error control coding. So one is block codes and other is convolutional codes. So block codes are a block of some check bits are systematically added to the message bits. Okay, so block అనేది ఒక సెట్ అన్నమాట. A block of or a group of some check bits. అంటే for example, the number of check bits be some r number of check bits అని చెప్పారనుకోండి. So r number of check bits are systematically added to k number of message bits to form n bit code word. So n bit code word. So n is equal to k plus r. K number of message bits and r number of check bits. So like that we can construct a code word. Code word is of size n. Okay, actually you can see here. I will show you. See here, you can observe the code word. Here this is a linear block code and code word, this is a code word. Code word is of size n. So a group of code words, this type of code words are generated by the channel encoder. So ఇలా ఉంటాయమ్మా. So each code word consists of n number of bits where n is some k plus r, where k is number of message bits and r is the number of redundancy bits or check bits added by the channel encoder. So where n is some k plus r. So similarly, how many code words you can see? Based on the combinations of message bits. For example, I said you there are 4 message bits. Then how many combinations are there? 2 power 4, that is 16 possible combinations of message bits are there. So for that 16 combinations of message bits, we have this many combinations of check bits. Okay, so how many check bits are added? For example, R, let us take it as 3. 3 check bits are added. Then the code word consists of 7 number of bits. 4 message bits and R check bits at 3 check bits. So if I said you number of message bits are 4 and check bits 3 and చెప్పేటప్పుడు, then the code word consists of, each code word consists of 7 bits. Okay. So similarly, we can design multiple number of code words by using channel encoder technique. And here a block of like r number of check bits are added systematically to the k number of message bits. That's why this is called as, that's why you can see this type of generation of code words is generally called as block codes. Block and edukanarma, it is a block of code words. Okay, a block of r check bits are added to a block of k message bits. That's why it is called as block code. But why it is called as linear? The term linear represents that, see here, this is a linear block code. The term linear represents that the sum of any 2 code words is equal to the third code word. Linear ante entama? It is linear block code. Block code ante a block of r check bits are added to block of k message bits systematically. Okay, that's why it is called as block codes. But block codes are of 2 types. One is linear block code and other is cyclic codes అని చెప్పారు. So you can see the PPT here. So in the PPT I told you there are 2 kinds of error controlling techniques. That is channel encoding techniques. One is block code and other is convolutional code. So block codes are of 2 types. One is linear block codes and other one is cyclic codes. Okay, and the second kind of channel encoding techniques are convolutional codes. Convolutional codes. This is a part B of your 5th chapter. In part A, you will study linear block codes and cyclic codes. Okay. Now, let us move to the next slide. So here already I told you block codes usually in the form of n comma k block code. So n is the number of bits in the code word. Already I have shown you. What is n? N is the number of bits present in the code word. How many bits are there? K plus R. K number of message bits, R number of check bits. Okay. So the same I mentioned here. It is usually in the form of n comma k block code, where n is the number of bits of the code word and k is the number of bits for the binary message. To generate n comma k block code, the channel encoder accepts the information in successive k blocks. So R number of check bits are added to successively to k bit blocks or k bit message, k message bits. Okay, so for each block add n minus k redundant bits. So here what is n minus k? N minus k represents the check bits. So which is denoted with a variable small r. With a variable small r. So here n comma k block code. Here first n represents the number of, please listen carefully. N comma k block code. In this n comma k block code, n represents the number of bits in the code word. And k represents the number of bits present in the, or you can say in the message. Number of bits for the binary message. And n minus k. So how many check bits will be added to k number of message bits? N minus k. For each block, n minus k redundant bits are added. For each block, n minus k redundant bits are added to k message bits to produce an encoded block of n bits called code word. So here in multiple number of code words will be generated, and each code word consists of k number of message bits followed by k number of message bits followed by n minus k check bits. So how many check bits are there? R number of check bits are there. So n minus k redundant bits are algebraically related to k message bits. Okay, so let us see how it is related. The channel encoder produces bits at a rate called the channel data rate. So what is the channel data rate? R naught. R suffix some R naught. R naught is equal to n by k multiplied by Rs, where R represents the information rate or the bit rate. So Rs represents the information rate of the source, or you can say bit rate of the source. Okay, and R naught represents the data rate. Okay, channel data rate. Okay, here R naught, that is the channel data rate, is related to bit rate of the information source, as R naught is equal to n by k into Rs, where n is the length of code word and k is the length of message bits. K is the number of message bits present in the message, and n is the number of bits present in the code word, or you can simply say n as a code word length and k is the message length, and n minus k is the length of check bits. Okay, and n minus k is the length of check bits. Check bits are also called as redundant bits because these check bits increases the redundancy. Okay, so channel encoder produces bits at a rate called the channel data rate. So here R naught represents the channel data rate. It is related to source data rate, as R naught is equal to n by k into Rs, whereas n is the code word length and k is the message length. K is the message length. Okay. Actually, this is not necessary. Okay, anyhow, the forward error correction codes, already I told you, these are nothing but our channel encoding techniques. Here you can say for each successive k message bits, a block of message bits, and each block will add n minus k redundant bits to produce an encoded block of n bits called code word. So whatever I said to you, the same I have mentioned here. So the channel encoder just accepts the message data bits in the successive k bit blocks and add each block and add n minus k redundant bits to each successive k bit blocks to generate n bit code word. Okay, and the channel decoder, what it will do, it will use the redundancy to decide and to recover the number of message bits. Okay, so this is about our forward error correction, and generally here this channel encoding process as well as the decoding process will identify the forward error bits. The detection and correction will be held by the channel encoding process. Okay, and in the decoder we will just reconstruct the message bits. Okay, so here you can see. So whether in this case, whether the decoding of the received code word is successful or not, but the receiver does not perform further processing. Okay, if an error is detected in the transmitted code word, the receiver does not request for retransmission of the corrected code word. Okay, so if there is any error identified or detected in the transmitted code word, the receiver does not request for retransmission of corrupted code word. Okay, so if the error is detected, that is the responsibility of the transmitter to detect and correct it. So if it is transmitted the same, then the receiver does not request for the retransmission of corrupted code word. Okay, so automatic repeat request, there is another type of scheme where if for example, if the error is detected or identified, that the receiver sends a request to retransmit the corrupted code word. Okay, so in the forward error correction, the FEC scheme, in the FEC scheme, generally the receiver does not request for retransmission of the code word if an error is detected in the transmission, during transmission. But in the automatic repeat request scheme, so generally there are two types of schemes available for channel encoding process. And what this automatic repeat request scheme is that it will repeat the the transmission of the corrupted code word, and it sends a request automatically to the transmitter. If some data is identified, like if an error is identified at the transmitter. Okay, so generally there are three types of ARQ scheme: stop and wait, continuous ARQ with pullback, and continuous ARQ with selective repeat. Actually, you can read all these in data communication. Okay. Actually, these three are not necessary here. So stop and wait and just it will see whether the error is identified or not. Okay, and it will check whether any kind of acknowledgement is obtained from the receiver or not. Okay, and in the continuous ARQ, it's like automatically will every time without any acknowledgement, automatically the receiver sends back the data, sends back the request to retrieve the updated code word. Okay, and in this third one, continuous ARQ with selective repeat, is a combination of stop and wait and continuous ARQ with pullback. Okay, so it retransmits the code word which was incorrectly decoded. Okay, so whenever it was not properly decoded, then only it will request for the code word. Okay, otherwise it won't send any request to the transmitter section. Okay, these are the three types of ARQ schemes. So anyhow, you will study all these ARQ schemes and FEC schemes in the data communication subject. Okay, so now coming to our syllabus. linear block codes. Okay, so here n comma k block code indicates that it has n number of bits and k number of message bits. So for an n comma k block code, n represents the number of bits present in the code word and k represents the number of bits present in the message. Okay, and here these two should be satisfied for the linear block codes. Already I told you block codes are of two types. Okay, block codes are of two types. Ikkada cheppam kadamma already. Block codes are of two types, linear block codes and cyclic codes. Now let us start with the linear block codes. Okay, this is linear block code. If you observe the first point, n comma k block code. So general block code ante enti? It is a combination of n code words. Okay, so where code word length is n, it has n number of bits, where n is equal to k plus r, where k is the number of message bits and r is the number of check bits. Okay, a code is set to, second point is here the term linear. Linear represents that if any two code words in the code. Okay, so linear ante already ikkada cheppanu kadamma enti, that the two code words. Here the term linear represents that the sum of any two code words. So if you take any two successive or any two code words is equal to the third code word. So then you can say that this kind of block code is linear. So a block code is said to be linear when the sum of any two code words in the in the process is equal to the third code word. So then you can say that the type of block coding is said to be linear. Okay, so here sum is not the direct addition. Here sum is not the direct addition. It is a modulo to arithmetic addition. So I can say that take the XOR of any two code words, you can get the third code word. So here what the term linear represents? Linear represents that the sum of any two code words is equal to the third code word. Sum represents the modulo to arithmetic, not the normal addition. We can take example as some XOR operation. So a code is said to be linear if any two code words in the code can be added in modulo to arithmetic to produce a third code word in the same code. So what is a code vector? What is a code vector? So here we can visualize the n-bit code words. So if you visualize the n-bit code words in an n-dimensional space, so take n dimensions and represent these n-bit code words. Okay. So please visualize n-bit code words in a n-dimensional space. Okay, as a vector whose elements have coordinates equal to the number of bits in the code word. Okay, so how many bits are there in the code word? N number of bits. Okay, so if I said you the code word is 101, then because it is a vector notation, please represent as 101 inside the some brackets. Okay, and please remember that these 3 bits are once again the combination of certain number of message bits followed by some number of check bits. Okay, now let us see the matrix representation of block codes. Okay, and here we are considering that the number of message bits. So take a block of k message bits. So how many message bits are there? K number of message bits are there, and we are representing it as 1 by k matrix. So message bits, how many message bits are there? K number of message bits are there. So please consider it as a 1 by k matrix. So message bits, the matrix size of message bits is 1 by k. Please remember that. And the matrix size of code word is 1 by n. So matrix size of messages is 1 by k, and the matrix size of code word is 1 by n. Okay. So now if you observe the modulo 2 operation, already I told you these linear block codes, the sum of, or you can say the modulo 2 addition of any two code words is equal to the third code word. Then it is called as linear block codes. Okay, let us see what is modulo 2 addition. So here you can see it follows the XOR operation. So the encoding and decoding functions involve the binary arithmetic operation of modulo 2. It is not the direct addition. Please remember that the sum of any two code words is equal to the third code word enter. Here sum does not refer the normal addition. It refers the modulo 2 addition. So here if you observe the relation here, please observe the modulo 2 addition. It obeys the XOR operation. So if both the inputs are zeros, then output is 0. If both the inputs are 1, then also the output is 0. So for same inputs, output is 0. For different inputs, output is 1. This is the XOR operation. And this is a modulo 2 multiplication. Okay, but in general, these block codes are said to be linear only when the modulo 2 addition of any two code words is equal to the third code word. So if you see the figure here, take any code word of length n, take two code words. And if you take the modulo 2 addition of these two code words, you will get the third code word in the linear block codes. Okay. So this is the modulo 2 multiplication, and here the term linear only refers when two code words are, when the modulo 2 addition of any two code words lead to the third code word, then it is called as linear block code. Okay. Here you can see, so this is a repetition code. This is you can see like one of the kind of linear block code, which is a repetition code. Here 5,1 repetition code. This is like one of the type of linear block code. So additional n minus k. So you can see n minus k number of bits. These are the redundancy bits. Okay, n minus k are generally called as a redundancy bits. Now specifically, if you observe the 5,1 repetition code, 5 minus 1, that is 4 bits. These are added to the binary message to form a code word. Okay, so for example, you have two code words. So you can see two code words at 4 bits add chestam. 4 bits are identically, 4 bits are added here. Okay, so 4 bits are added with a new check bit. Okay. Here if you observe, okay, we can continue the linear block codes concept in the next class. Okay, so the matrix representation. And one more thing is, I have uploaded this PDF. I have uploaded the PDF of 5th chapter in your Teams link. Please go through that. So here you can see files. So I have directly uploaded. So in unit 5, I have uploaded the PDF. Please go through that PDF. I request you all the students to simultaneously go through this PDF. This PDF is enough for your examinations. So I will submit you the PPT, but that PPT consists of all the like background concepts and foreground concepts also. But this PDF is enough for your examination point of view. So I request all the students to please download and keep it in your desktop, so that during exams it will be okay. I have uploaded, please check it. And meanwhile, I will upload the PPT to you. Okay. So any doubts in the today's class? In the today's class, I have only introduced the concepts of channel encoding techniques. Okay. And the next class onwards, we can clearly go through the matrix description of linear block codes. So any doubts in the today's class? Okay. Okay, I took attendance. Now you can leave. If you have any doubts, you can ask.